What a fantastic reception. I apologize for the color scheme. I have a little bit of color blindness, so fortunately I don't notice it, but you will. So I will talk about different galaxies across cosmic time. I am using this opportunity to show you my kaleidoscopic graphs. They have the ability to span large redshift ranges and luminosity ranges, so feel free to disagree with my choices there. But what I want to show you first is this beautiful image. So I met TC at the conference in the JCMT, JCMT user meeting last week, and nobody showed this image, which is one of the most beautiful images that I've ever seen. Some people see a dog in it that just threw up. What I instead see in it is 5 sources. This is the same field as that was observed by Hubble a couple of years before. This is the Hubble Deep Field. Hopefully you're all familiar. 10 days straight, Hubble observed a small piece of sky without anything in it. 3,000 to 6,000 galaxies, all different cosmological distances, different cosmological evolution states, elliptical galaxies, some spiral-looking stuff, nearby galaxies, faraway galaxies, many different things. Then observing the same patch of sky with essentially 50 temperature sensors looking at the dust emission from these galaxies, mapping this area for 50 hours, revealed only 5 blobs. When you look at these very bright blobs, you don't see any emission, any bright emitting galaxies. It took us James Webb to detect this guy, and even detecting the dust emission from, or the optical emission from these guys has turned out to be really difficult. Now, none of this should matter to galaxy evolution if it weren't for the fact that if you count the photons in this image and you count the photons in that image and you convert for the difference in energy, they're the same amount of energy being emitted. If you want to understand how galaxies evolve across cosmic time, you need both a picture of the optical, or the near infrared, and a picture of the submillimeter or the dust emission. These galaxies are all at quite high redshift, redshift 5.5, discovered in 1997, so really far away back in the time. So this shows us dust, and dust is good for many things. In part, we can detect faraway galaxies. In part as well, it helps us form stars. It allows an easy cooling transition from these warm gas clouds that can't radiate their energy away, and then they hit a dust molecule. Then the dust molecule ever so slightly heats up and emits it at long wavelengths, escaping these gas clouds and turning efficiently into stars. A lot of chemistry. I work together in Chalmers with chemists. It is an experience like no other. They have different kinds of assumptions that make me go crazy, and our assumptions on what dust does at high redshift make them go crazy. So we have a good partnership. Dust is key to storing most of the metals in the universe. If you want to understand planet formation, it is important to understand where the bulk of your dust is in systems. Throughout this talk, I will talk about essentially somewhere around here, so when reionization, etc. was happening, the first galaxies, all the way to the present day, and try to guide you through this kaleidoscopic journey of what galaxies look like when we look for their dust emission in the distant universe, all the way from, let's say, 300 million years after the Big Bang to right around now, which is 230 almost. So, even pre-JWST, we were struggling to find a coherent picture of dust across cosmic time. So what you see in these blue data points is what we managed to do with Hubble. These deep fields map out how many stars are being formed across each epoch of cosmic time as a function of the volume, and compare that to the submillimeter. And submillimeter struggles with getting a homogeneous volume and struggles with correcting for lensing. But what we're really dealing with is sensitivity limits, able to probe out large enough volumes and understanding the population well enough out to very high redshift. Now with ALMA, deep surveys, the work that TC is doing, the work that Hiddo is also doing, we're able to push it out to redshifts of 6 reasonably accurately, but we're really struggling to map out what dust is doing at the highest redshifts. And this is even considering the fact that we live in a miracle universe. We have the ability to detect galaxies in the submillimeter with so much ease relative to these people using James Webb or X-ray or radio. What you see here is a typical spectrum of a galaxy that's just being pushed away further and further to higher redshift. Same luminosity galaxy, but at different redshift epochs. So one at redshift 0.1, of course very bright, very close to us, but at 0.5 already, you can see that this galaxy is getting fainter, and as it being pushed further and further and further away, it becomes fainter and fainter and fainter, the same way you have with a candle, I guess, on a table being further away. But what also happens is that the spectrum gets redshifted, and as the galaxy is being pushed further and further away, the emission shifts to the red for you guys, to this direction, and it's starting to overtake the spectrum in its cosmological dimming. So you have this perfect region here in the submillimeter where if you just take a single flux cut, you basically know the luminosity of the galaxy that you're looking at. So for a given flux, regardless of the redshift of the galaxy, if it's redshift 10 or if it's redshift 1 or if it's redshift 5, you know that the luminosity of a 1 millijansky galaxy at 850 should be, let's say, 10 to the power 12, 10 to the power 11 or so. Even given this cosmological good fortune, we are struggling to map out the universe deep enough, far enough through technological means. So one of the ways that we want to look for the furthest away dust is through the submillimeter, but that's difficult. Instead, what we have to rely on in the very, very far away universe beyond 600 million years is the optical attenuation curve. Here is a redshift 2 galaxy that has been mapped really beautifully in both the optical and in the submillimeter. And you can see that while the typical stellar emission in blue gets emitted like that, very, very sharp curve here where most of the light gets absorbed due to the Lyman break, and it gets attenuated by dust, so more of the blue part gets absorbed, eaten up by the dust, less of the red part. So you can see that the slope really changes from here to there. And now all this emitted, the stuff that gets absorbed by dust gets re-emitted in the submillimeter, and we have this energy balance that's occurring. So we're looking at these galaxies in the very early universe, and we can see different features of the dust obscuration. So here you even see a feature of the dust itself, the carbonaceous dust, but you also see in different types of profiles, you can see these attenuation curves of dust existing beyond the redshift of 8.3. But then we go look for the dust emission of these galaxies. Here's a guy at redshift 12 where we looked for 16 hours with ALMA, and we find very, very little dust emission here in this source, very little dust emission. So to combat this, together with HIDO, we compiled a list of galaxies with observations in the submillimeter that you can see here reflected against different SEDs. And you can see that we get really deep, all these black points are really deep upper limits that we managed to get from, in total, something like 150 hours of ALMA time, something like 100 hours of NOEMA time, that we can combine into a single spectrum to see how deep the detection limits are that we can currently put down with ALMA. So to introduce you softly to the kaleidoscopic image, what we see here is a function of redshift, or essentially the age of the universe. So even at 300 million years after the Big Bang, we don't detect any dust. Moving further and further, we still don't detect any dust, and we can place these really deep upper limits in the capability of ALMA to go look for dust, but not see any dust emission yet. I compare this to some trend lines that we got from models that are initially built on the Millennium simulation. And if you assume a certain efficiency of growing dust, assuming supernovas, maybe some small contribution from AGB stars, you can assume a certain dust to stellar mass ratio, and you can see that that's sort of in line with the most massive galaxies that we expect to exist at that universe, that it's kind of understandable that we're not yet detecting dust in 300 million years after the Big Bang. The processes that take time to build up stellar mass in galaxies and the processes that build up dust inside of these massive stellar environments, they simply take a lot of time to build up the dust. But we can compare this to many different models that predict dust obscuration, the dust production. So particularly if you focus on the right-hand side, you can see as a function of stellar mass that we're really pushing down. These are the individual data points. In red, you can see the stacks that we've been recently working on. We're really approaching the limits of what these models are predicting to exist in the early universe. So not only are we seeing that these galaxies are simply quite low mass, also we are approaching the similar timescale as it takes to simply form dust. So even though you might have a cloud of a lot of metals, they still need to coagulate into dust and get radiated to be able to be visible. And apparently 300 to 600 million years, it is quite difficult to efficiently form large quantities of dust. That's what we're seeing in this image now. And as James Webb continues to detect more dusty galaxies, and as ALMA continues to follow up these galaxies, we can push these limits deeper and deeper and see if we can really break even these very inefficient dust production models out to the early universe. It's a function of cosmic time again. Here you can see furthest away non-detection of dust that we have. You can see that we're really approaching these very inefficient dust production models. Here are observations that are clear detections from surveys such as Rebels. A little bit further, there's Alpine as well. They show quite efficient production of dust, and yet, since the universe appears to be one coherent system, we need to understand how there isn't any dust here and there is dust there. So there needs to be a very steep, almost step-like function in the production of dust in the early universe. And by stacking and continuously stacking incoming ALMA data, currently we're at about 100 to 150 hours of ALMA time, but in the next few years, as we're following this up, we should be pushing this further and further down until hopefully we start to detect dust. Now I want to introduce you to my favorite galaxy, except for the Milky Way because I live there, but this is MAX 0416Y1, or Y1 if you're friendly to it. And finally we managed to collect 5 hours of band 9 time, because over the past few years we've been gathering this suspected feeling that this might be a very, very warm galaxy. So currently we have this band 9 data point, but previously we only had these 3 data points here that pictured the spectrum of this galaxy to be rapidly increasing. And instead what we're looking at, and confirmed by the band 9 data, is that this is a 90 Kelvin or 86 Kelvin dust temperature, dusty body in the early universe. This means that the galaxy that is the furthest away direct detection of dust that we have in the early universe is a ULIRG. So we see nothing, we see no dust production, and suddenly we see a relatively minor amount of dust emitting a very large amount of infrared emission, very high dust obscuration amounts, something like 93% of its emission is dust obscured by a very small amount of spatial dust that you need. But because of its dust temperature being so high, it means that the star formation rate of this galaxy is something like 200-300 solar masses per year. James Webb, again, continues to amaze us, and if we look at this source in resolved James Webb imaging, you can see it consists of quite a complex morphology. So as we go to longer wavelengths, of course, the PSF worsens ever so slightly, but you can already see 2 to 3 components in it. And you can overlay these components and see what part of the galaxy then is reddened by the dust and what part of it doesn't appear to have any dust obscuration at all. This is quantified by something called the parameter UV beta, so essentially the slope, the redness that we get from these, how much of the stars are being obscured by the dust. And as we go to bluer, it means less obscuration. If we are looking at the very red part, it means that there is a lot of dust there. The dust is doing a lot of reddening, and a lot of the blue is removed, but a lot of the red is maintained. And overlaid, you can see what we see with ALMA. ALMA can look at about a spatial scale of about 200 parsec or so really the scale of individual large dust clouds inside this source. And you can see that some of the peak emission that we see with ALMA and the regions where James Webb is actually predicting that there shouldn't be too much obscuration appear to be overlapping. And this means that the source itself is likely more complex than we can even resolve with James Webb and with ALMA, that there is substructure within these regions that is doing, for example, some dust destruction as well, and also that the obscuration rate of this source again is 93%. So we cannot rely just on the optical perspective to gather the amount of obscuration. If we had assumed that this was just a beta UV of -2 or -1.8 or so, we wouldn't have assumed that this guy would be hiding a Euler level of dust obscuration. We need to go to interferometers and need to go to the survey depth of ALMA to be able to reveal objects like this. So, as I previously showed you, we're not detecting any dust here, and we really need efficient grain growth to approach this range. But now when we plot Y1, we find that we're really pushing this very high line. This is thus slightly in contradiction with models, but it is only in contradiction with models because its dust temperature is not 50 Kelvin, but its dust temperature is 85 Kelvin or so. So this high infrared luminosity is being created by the high dust temperature, and this is something that we desperately need to find out over larger samples, whether it's common that the first burst of dust we see in the early universe could be due to very warm dust and actually a very high obscuration, even though the dust masses themselves remain very low.
Tom,
please.
At that redshift, the microwave background is about 30 Kelvin.
Exactly.
So that means a third of the heating is caused by microwave background rather than star formation. Is that correct?
No, it doesn't work linearly. I mean, fortunately, I don't know what the right adverb is. Maybe I skip forward one slide. You can see here, for example, that what we see here in this grayed out region is the CMB temperature increasing linearly for a more compact universe, right? It's simply redshift times the current CMB temperature. And you can see that we are so far above it that the CMB effect is very little. But the contribution that a single CMB photon has, let's say 30 Kelvin photon has on even a 40 Kelvin body, is very minimal because it scales with temperature to the power either 4 or 6, depending on how you include the quantum effects of the dust contributing to the source. So indeed it is true that some of the rebel sources, and particularly some of the sources that both Joris Wittstock and Hiddo Algera also look at, they have dust temperatures that can really approach the floor. It's hard to get dust temperatures underneath the CMB. Some small regions of the local universe are sub-CMB temperatures, but for dust, the floor is really the CMB temperature. That's not the problem and not the reason that we're having this super warm dust in the early universe. That's likely more due to very young stellar populations and dust being spatially very closely associated to one another. Very little shielding, so the majority of the dust is also directly seeing all of the harsh radiation fields, boosting the dust temperature very high, and thus also the obscuration fraction being very high. Does that answer the question? Kind of skipped over the kinematics, but I'll leave that as it is. Instead, also many people are trying different approaches to try and correct for this dust. It's hard to get, 20 or 40 hours of ALMA time on a single galaxy when we have now hundreds of galaxies at redshift 8 that desperately require this. So there are both geometry arguments and C+ based arguments that this source was indeed already this hot. Of course, the only smoking gun evidence that we can have is by looking at the spectrum. And this is something that I started working on already in 2021. So this is data that we published in 2021, and some recent work, I think also at Taiwan, has been done on this galaxy. This is one of the first detections of dust beyond a redshift of 7. In 2015, I think Darach Watson published a really nice result showing that this was a very massive body of dust already in the epoch of reionization. I think it was this data point that was published. Then the accurate spectroscopic redshift was measured. And then more follow-up was done to reveal different emission lines of this source. But while also targeting the emission lines, it became also possible to target the dust continuum. And what you can see in this beautiful red line here is or filled area, is what we can do when we have the band 9 data. So this is about an hour of band 9 at a redshift of 7 or so, allowing us to fully characterize the dusty body. What you can see in these dashed curves here instead is the unknowingness that we have about the universe without the band 9. The dust temperature can be either incredibly hot or it can be incredibly cold, but we don't know until we measure completely on the other side of the dusty spectrum. The amount of star formation is simply the area under the curve. You could just plot a triangle under this and do almost as good a job as fitting a nice modified black body to it. to get an estimate of the amount of star formation being hidden underneath. But you can imagine if we plot a triangle under something that goes all the way up to here with a temperature of 300 Kelvin or something, that is a star formation above 1,000 solar masses per year and very unphysical. So we need a lot of short wavelength observations on these distant galaxies to constrain the amount of area underneath these black body curves. HIDO also has a really nice example. I'd be remiss to show it. This is, I think, Rebels 25, one of the best sources that were detected in the large program with ALMA. And by tracing the area under this curve completely, they find a very cold dust temperature and a very large dusty body. This is close to approaching CMB temperatures, still a little while away, but it is a very, very massive dusty body. And only by looking at the short wavelength data and getting this full perspective on the dusty body can we get an understanding of what dust is doing in the early universe. So, long story short, we don't detect any dust here. But if we project efficient the most massive galaxies found in these models and efficient dust growth, we can explain why one. Then there's also these Lyman break galaxies like Alpine and Rebels, little red dots that I maybe mistakenly put in here as if they are galaxies, and these Lyman break galaxies that lie sort of on par as the earliest detection of dust, but they have a very large, massive amount of dust already, but a much lower lower dust temperature. So their relative contribution to the far infrared background and cosmic star formation rate can be a little bit lower. That said, still a large part of these galaxies remain dust obscured. So this work combined both the work of Jorge Zavala and Bowens. I think HIDO also did a very nice job on measuring the star formation rate density, so the amount of star formation that we are able to now probe with these deep surveys. I think this work comes from some deep surveys of Subaru detected galaxies, and we're able to probe out how much of the emission is dust obscured in the early universe, finding about 50%. So we're even out to a redshift of 6 or 7, 50% of our star formation rate is dust obscured. But that immediately brings me to the point that how are we finding these galaxies in the first place? Like, we can do these big area maps with, for example, Herschel, SPT, with JCMT to look for dust emitting galaxies, but those are the icebergs, the tip of the iceberg essentially. And underneath that is an entire population. But if we use JWST, we're also going to find only the ones that are optically very bright. Again, not the ones that are the most dust rich. And instead, we developed this plan to follow up a whole bunch of galaxies that are found close to quasar companion galaxies instead. So even the SDSS was managing to detect quasars out to a redshift of 6 or so, and by following up these quasar sources with ALMA and C+, it turned out that many of them tended to host submillimeter galaxies right next door to them. So likely these are in some form of overdense environments, maybe some slight enhancement in the star formation rate efficiency in these regions. But even then, the amount of galaxies that were found in these deep surveys essentially blind, and only through C+ emission, making it also quite an effective tracer of looking for galaxies in the early universe. So following this up with a scandalous 40 hours of band 8 time with ALMA, we managed to find very little dust in these galaxies at warm temperatures, but quite a deep amount of dust at longer wavelengths, meaning that in these moderately overdense environments, it could be that the dust temperatures are quite low, but the dust masses are very high, and finding such galaxies in optical surveys is near impossible because they have a large amount of dust and are thus strongly dust obscured, and finding them in submillimeter fields is also really difficult because their flux density is underneath what currently can be detected with 20-meter class submillimeter telescopes. Again, this is work done together with HIDO, but a takeaway from this is that we managed to make a very, very deep stacked image and find very little dust in these quasar companion galaxies. So placing them on our kaleidoscopic image of dust across cosmic time, you can see that they lie below Lyman break galaxies, but with very large dust masses and quite low infrared luminosities. Yet, if we want to uncover the full mountain that is the dust obscured universe, they are a key component in building towards a full understanding of the dust-obscured universe. Effectively, this has all been part in my postdoc, but my true passion came from the fact that I worked on the Herschel Space Telescope, which was a 3.5 meter class telescope launched into space together with the Planck CMB telescope, and it managed to map 1,000 square degrees. So I think currently JCMT is around mapping 10 square degrees or so. So this is about a factor of 100 times deeper. By the time Herschel launched, about 100 or 200 SMGs were known. Then Herschel observed 2 very large fields and detected over 1 million galaxies. So we have a very, very deep probe across cosmic time using sub-millimeter wavelengths that are really hard to reach from Earth. And part of my PhD project was following up the 250 brightest galaxies of these. And one of the ways that we managed to do that was with ALMA. This is a nice illustration of what we managed to do when we did a really deep survey to look for the CO emission lines of these galaxies to finally get their cosmological distances, their spectroscopic redshifts. This already tells us quite a lot. I mean, it's just a graphical depiction of the data that's all been normalized to the 0 velocity and shown in aligned in the x-axis. But what you can already see is that even though these are all selected from about the 30th of the night sky, you can see that there's a large variation in different types of properties that we see across these galaxies. I mean, this near Mount Everest looking guy is very, very broad, very, very wide galaxy, likely indicative of a very massive system. There are some of these that show these double-pronged profiles, maybe a merging galaxy that remains unresolved by ALMA, or instead a spiral galaxy or so that is being also seen as a single point source by ALMA. But there's also these really tiny, almost cute-looking spectra of galaxies that imply very compact galaxies. And instead what we see is just a large diversity in the type of galaxies that are being selected when we look in the sub-millimeter.
Is it true that there are more red components than blue components?
Ah, okay, that there's a bias towards having them to the right-hand side than to the left-hand side? No, the spectra, I think, are fitted simply to the peak flux. So, yeah, I don't know if there would be a reason, a physical reason why there would be more on the right-hand side. It does look that way, doesn't it? Yeah. I also truncate a lot of the spectra, and I don't include them if they fall close to the edge of the band, because then you had a lot of like these flat lines that kind of ruined the aesthetics. But we could play a little trick with these galaxies, and we can throw them all in a giant stack. We discovered that a lot of them actually had larger full-width Hopf maxima than we were expecting initially. And looking for an explanation for this in unresolved data can be a little tricky. So we stacked the ones with very small full-width Hopf maxima and the ones with very broad full-width Hopf maxima. And if you are willing to squint your eyes a little bit, maybe you will agree that this looks a little bit more double-pronged, a little bit less double-pronged, and that this looks almost nearly completely Gaussian. Again, they're all normalized to the same full-width Hopf maxima before stacking, but the idea being that the majority of the large full-width Hopf maxima and the diversity that we see could either be due to grand design spirals or unresolved mergers in these 2 to 3 arc-second beams that we're doing with ALMA. It's important to include these galaxies because they are the ones that really dominate this picture of dust-obscured star formation in the early universe. So at around cosmic noon, there you have this really peak area of that's dominated by dusty star-forming galaxies. There's also hot dogs in there, the ones that are discovered, for example, by ALES, by JCMT, even 450 micron selected galaxies, they lie slightly below here. They really dominate and represent the peak of galaxy evolution and dust production in a single system. And then afterwards, as we move towards more and more here, we see that a lot of dust destruction is really dominating the picture of the dust evolution. A lot of these galaxies rapidly deplete their existing dust reservoirs due to the non-regeneration of dust in these systems, and instead in the local universe there doesn't exist a single galaxy above 10 to the power 13 in LIR. So that means that if we want to understand the most massive amounts of buildup of dust, we should really look at cosmic noon. This has already been known since we looked at these JCMT images, but these really represent the peak of the proverbial iceberg of dust evolution. I'd be remiss if I didn't show you a couple of my favorites. This is my talk, so I get to do what I want. SDP81 is a very, very famous lensed galaxy, and I want to show you this image. And when I was, I think I was first year PhD student, it took a good 6 weeks before I believed that this was a real observation and not a simulation of what the lensed galaxy should look like. Previously, yeah, this room is not big enough to show you the Herschel beam that detected this galaxy. I think we would need to go to, no, not to the next building, but it is, the resolution that we see here is something like 0.01 arc second or so, or 0.03 arc second. Meanwhile, the Herschel beam that selected this source is 36 arc seconds. So that's, calculate with me, 3 orders of magnitude difference in what ALMA can do and what a single dish in space can do. But because this is a geometric effect, a foreground lens that you can see in blue here, I think from a Hubble image, is warping the light from a background source in such a way that we see it as this beautiful Einstein ring. But because this is just a geometric effect depending solely on the mass of the foreground, you can invert this effect and you can have this beautiful image here of what this source looks like at a redshift of 3. So this is a resolution somewhere between 30 and 50 parsec or so, where you can see these individual gas clumps inside this galaxy. If you calculate the Toomre parameter, so the stability of the system, it appears to be rapidly collapsing onto itself. That doesn't really have a lot of evidence of merging, although it could be a late stage merger, but this could also just be a normal galaxy that has some sort of violent disk collapse that triggers this burst of star formation and dust production, and therefore we see it with Herschel in such magnificent beauty. In fact, many of these galaxies, if we look around them, we see that they have a lot of companions next to them. So we look in the field and then we see 1 or 2 or 3 nearby galaxies that we weren't even selecting towards. So what I show you here is the fraction of multiplicity. If every galaxy has a brother next to it, the value would be 1. If all these galaxies are isolated galaxies, the value would be 0. Meanwhile, if I just randomly point ALMA, there is for a certain flux limit just a chance that I will randomly see a galaxy in my field. That's shown by these lines moving up. So if my line moving up is to the left of my source, I have more galaxies than I was expecting. This is true for all these deep fields that we do on these dusty star forming galaxies. So in red and in blue are the deep surveys that I've worked on together with people. Similarly, ALES as well, also very famous for having several more sources than we expect in the fields when we follow them up with ALMA. This led us to doing some nice work with JCMT. JCMT has this ability to, instead of while ALMA has a single pixel on the sky and 60 or so or 43 telescopes at the same time looking at that small piece of sky, JCMT has about 3,000 of these pixels on the sky and can rapidly map very deeply large areas. So here you see something like a 7 by 7 arc minute field that has been seen by JCMT, and you can see many different galaxies close to this central source. Then we went to the NOEMA interferometer, which is in the north, and this source is also in the north, so that worked out nicely, to follow up the galaxies close to it and see if they are spectroscopically associated to the central galaxy. We found that actually 2/3 of the sources that we saw were not associated. They were just chance alignments. We just happened to detect them along the line of sight. If you recall, I showed you the K correction, so these spectra that were overtaking each other, meaning if I look at a single 850 micron, the redshift could be 1, the redshift could be 10, the redshift could be 5. The same is true for if I do a field like this. We have the entire universe to allow for source confusion in submillimeter fields. So getting the statistical value really requires us to first go to interferometers to get all these beautiful spectra of the CO, then we get also the molecular gas, but we also get the information of this is an overdense field, it's confirmed spectroscopically. And now we can fully trust that indeed this field saw a spectroscopically detected cosmic overdensity. A few days ago at the JCMT user meeting, I already showed this image. These are all the survey fields, I mean, particularly in the north and the south have been done with Apex, but the north majority has been done with the JCMT that has been followed up these fields. But the amount of spectroscopic follow-up that each of these fields has is in total around 8. So in total, I show you around 250 fields here. Only 8 of them have been followed up spectroscopically to confirm that what we're looking at is indeed a verified cosmological overdensity. And actually, that is a big opportunity gap that we're leaving right in the open, because if you can show that the total mass that you see in these dusty galaxies exceeds what can be produced by lambda CDM, you can just take the entire lambda CDM and take it to the bin and chuck it in there. If we can show that we can break lambda CDM with a protocluster, particularly at higher redshift, it is possible to use protoclusters to test the fundamental buildup of the largest coherent structures in the universe. Here you can see an example that particularly the highest redshift galaxies, the highest redshift overdensities, here's the number of counterparts that are found in a field. Many of these are already in tension with lambda CDM. We need to go and follow them up spectroscopically to either see that this point disappointingly falls here, or again, the trash bin example of lambda CDM. I'm going a little over time, so I'm going to skip a little bit. Again, this coherent picture of dust evolution in the early universe, where we can now really try to push and start to understand how dust is being formed in the early universe, is giving us a lot of cool examples of science that we can do. But also this little triangle here that's completely devoid of galaxies is quite interesting, because if we understand how dust is being destroyed, that is also necessary to understand, for example, maybe why we're not seeing any dust here, even though, you know, many of these points fall underneath this line. And one of the ways to do that is by looking at these again, here I show you what the typical Herschel source looks like. This is a single pixel. Single pixel is larger than this field of view to understand that these galaxies are both lensed and to understand what the internal properties of these galaxies are doing. So one way of doing that is by looking at for foreground lenses using statistical analysis. We managed to do that on a small sample of galaxies with ALMA in 2024 based on earlier work across a 1/30th of the sky with Viking, or we go after high resolution imaging. But we encounter a very tricky issue with ALMA. If you want to follow up a nice spectral line with ALMA, you go to ALMA and you say, please look at this source, and it'll go like, okay, give me 20 minutes to set up my entire tuning. And then you spend 20 minutes, and then you look at this source, but it's crazy bright, so you only use 2 minutes of on source time on this source, and then you're like, oh, okay, and now I want to look at the other spectral line. Oh, okay, 20 minutes, 2 minutes on source. It's not a way of doing coherent science. And instead what you can do is you can say, within this phase center, calibrate once, and just visit all these sources for 2 minutes, very, very rapidly. Bam, 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 bam. And in that way, you can do in 1 hour, you can do, this is 16 fields, I think, in total. In total, 19 sources, maybe you can count faster than I, that you can see here. And again, the diversity that we saw in the spectroscopic data, you can now also see beautifully resolved. Here is one guy that's lensed by 2 foreground galaxies. Here's an accidental coffee cup stain that was left in this beautiful Einstein lens. This is a very, very wide, extended galaxy that spans over 20 kiloparsec that's completely dust obscured. This is a very, very narrow, very small lensed source. But we like pretty pictures, but we're scientists, so we put them in a graph. Here on the y-axis, you can see their size, and here you see the infrared, the intrinsic luminosity accounting for lensing, and you can see that they span over 3 orders of magnitude. So the diversity that you saw in the previous images, the diversity we saw in the 1D spectra, you can now see reflected by 3 orders of magnitude in surface star formation rate density. So the amount of star formation that these galaxies have per area varies tremendously. In other words, there are many, many, many ways of making a massive galaxy. I apologize, this is way too much data, but you can see that this order of magnitude reflects other galaxy samples, like for example the local galaxies shown in black here. They have also a similar diversity as these dusty star-forming selected galaxies. It is thus important to follow up comprehensively along large samples to capture this diversity and to also link where do these galaxies lie relative to their predecessors. Are crystal galaxies predestined to turn into dusty star-forming galaxies? How do galaxies evolve from redshift? 20, 14, 10, all the way to cosmic noon. A small little trick that we used during the quick sampling of the sky was to optimize the spectroscopic tuning of ALMA. So ALMA gives you full rights to just select a frequency in band 3 or a frequency in band 4, 5, 6, 7, 8. And now we also have 9 and 10 on these galaxies. And because we know the spectroscopic redshifts from our earlier surveys, we know exactly where to tune these observations to include as many spectral lines as possible. So simply by shifting our spectral windows a little bit, we can include the number of accidental spectral lines that we got by a factor of 3. This means that if you are doing a continuum survey and you have the spectroscopic redshift, it is scientific malpractice to not think about including spectral lines. My harsh opinion, feel free to disagree with me. In total, we managed to collect and target 64 spectral lines across bands 3 through 8, across 6.5 hours. 38 of them, CO lines. This is quite nice. You can already see this, this beautiful guy here. This is one of these coffee cup stains. A very beautifully detected line, 2 minutes on source time. And what we can do with this on source time is we can compare the amount of gas that we see and compare it to the star formation rate. This is so-called Schmidt-Kennicott law, the resolved star formation law that people say, and you can see where on the star formation track they lie. I mean, I know TC has done something very similar to this, but it allows us to ask a very fundamental question. These galaxies consist of a lot of gas, and this gas is forming stars very efficiently, or is forming stars. Do these galaxies simply just have many more gas? Many, like a single galaxy might be depicted by a single gas clump, and do these galaxies simply just have many more gas clouds that are forming gas equally efficiently? Or is it true that at high redshift, for whatever reason, a larger gas clump simply becomes more efficient at forming stars than a smaller gas clump is? So is a smaller gas clump less efficient than a big one? Is a fundamental question in galaxy evolution. And now we have the data to actually answer this. So here you see a galaxy that we can place these beautifully tessellated things on. This is work from my master student, soon to be PhD student in Chalmers, that managed to do these beautifully tessellated. Isn't this fantastic? He managed to make these tessellated apertures that he can place all across the sources and efficiently probe the Schmidt-Kennicott independently from one another and trace whether or not this scaling relation is simply linear or superlinear. And what we're seeing is that for the majority of these galaxies, it's superlinear, meaning that if you give me a larger gas clump at high redshift, I will form stars much more efficiently than several small gas clumps. This, if it was linear, it simply is a counting exercise. I have X amount of gas, I form stars at Y amount of speed. But now it means that I have a large amount of gas, I form stars at a very large amount of speed. Showing you in a graphical depiction, this is 23 galaxies. And we're really probing out very high gas densities. And we're showing now, for the first time at high redshift, that we can show that galaxy evolution is happening in an accelerated way in the early universe, happening on timescales that are proportional to the free fall time and not just similar to the more is simply more. But more is really a lot better at high redshift. I'm going to skip over a few things before coming to my conclusions. In Europe, currently we're developing this idea to think about what we want from our institutes in 2040. So to think about what we can do in 2040, maybe we should think and look back a little bit what we did 20 years ago or something. So Hubble was able to detect all the way to a redshift of, let's say 6 reliably, when I think it was Majolino detected some nice, or confirmed through the detection of C+, that Hubble indeed was managing to look at the redshift of 6. Then Takuya Hashimoto and Derek Watson showed that there is indeed dust at the redshift of 7, or this is even 9.1 in a in a Hubble detected galaxy. And then bam, James Webb happened. James Webb managed to detect galaxies all the way to redshift of 14, 14.5 if you believe the paper from a few days ago, redshift of 16 or so. And it can really probe the interstellar medium of these galaxies out to very high redshift. But that's not exactly true. It can look spectroscopically up to around a redshift of 6 if we're looking at H alpha, 8.5, 9 if we're looking at oxygen 3 as a tracer, and then afterwards we have to use MIRI, which is about a factor of 10 times less efficient at looking at the interstellar medium. To show you an example, this is redshift 12. This is GHZ2, spectacular name. But you can see very few faint features, and then suddenly here in MIRI in green, you can see that we capture these oxygen lines and H alpha lines that we need to do our interstellar medium analysis and understand the properties of these galaxies. But then we have to turn to ALMA and use the spectacular resolution, spectral resolution also that ALMA offers to really capture this oxygen 388 micron that we can look for all the way to redshift 40, 50 or so. For these galaxies. So looking forward and pushing into the future, I believe that if we want to make the new step with ALMA, we should look at the capabilities of resolving the kinematic nature of galaxies in Milky Way type galaxies all the way to the first 300 million years. This will give us numerous set of advantages. We can get super precise redshift, so we can study the neutral gas around these galaxies. We can measure the electron densities using different line ratios. We can test the dust production, something I care about. The IFU capabilities of James Webb are pretty rubbish. The resolution there is at best something like 60 kilometers per second if we're pushing it. Instead, ALMA gives us unlimited resolution if we're really just going for deeper integrations. And the opportunity space is there. We already know that there exist many more galaxies that we can detect, but this guy took us 2 hours to detect, but secretly it took us 12 hours to find the spectroscopic redshift of this guy with ALMA. Similarly, for GHZ2, it took us 8 hours of on-source time, but 24 hours by the time we had found the line. If we gain a sensitivity of a factor of 5, we suddenly open up the full potential space that is now being developed by James Webb. So when James Webb ceases operations in about 10-15 years, ALMA can go and really follow up these very, very deeply out to the early universe. Please look at our European website, but I also encourage you as the Taiwanese community to start up the discussions. What do we want ALMA to do in 2024? And if you have any questions about this or the previous stuff, let me know. Thank you.
What's in that picture?
Which one?
The telescope picture.
The telescope picture. Yeah, I don't know. I don't like this. Let me. Wow, I don't. Yeah, I don't know. I think they're. Yeah, I think they are upgraded versions of ALMA dishes, hypothesized perhaps. There are many different ideas that have been posited for future upgrades of ALMA, and it's not necessarily clear what type of dishes we would want, where exactly they would be placed. Yeah. Please.
For this varying star formation efficiency at high redshift, I wonder, have you seen similar trend in the local universe as well? Because I suspect that for Hilbert type galaxies, they are also gas rich, so presumably I would assume not high star formation.
Exactly. This is. Sorry, let me just skip through slides. So already what we saw in unresolved observations, such as Wang and Tacconi is that star formation efficiency is high in high redshift, and the same is being seen, for example, at the Fangs type galaxies that are more starburst. But it's very hard to get both a good constraint on the total star formation rate and on the gas content of these galaxies, so they're measuring it more through turbulence. They're also finding that star formation is enhanced, but typically that's merger driven. They find that there's a large fraction of mergers that are doing this, this boost in star formation efficiency, which might be different than ours because we see some merger evidence, but definitely not all of our galaxies are merger driven.
Could you go back to the redshift and mass plot, dust mass plot? Or this one? I'm just curious, at the higher redshift, in order to estimate the upper limits for the dust, you probably need to assume some temperature of the dust.
Yeah, we use 50 Kelvin, yeah.
I'm curious because, sorry, you also show the plot for the detected sources, there's actually a redshift trend, if I remember correctly. So I guess at higher redshift, you just adopt this trend and the temperature will be higher.
Yeah, it's
so
true.
The limits will go up or go down?
Oh, that's a good question. I think the limits in the dust mass will go up because at lower temperature, you can hide a lot more dust with a lower temperature in a galaxy and not detect it. So these values would go up. There is indeed a trend seen. There are some physical explanations as to why that it exists, but it's not necessarily a physical trend across all galaxies in a high redshift universe. So everybody is showing it as an empirical relation instead of as a fact that a high redshift galaxy is simply warmer. Maybe people disagree with this.
Well, again, I want to ask, like, why one is warm, but we haven't found any other galaxy that is this warm. So what are we doing wrong as observers? Why are we not finding them?
We're not going deep enough on galaxies in the transition range here. Maybe.
Just more depth.
Yeah, because as soon as you go into this region with these Rebels galaxies that are supermassive, you have such large volumes of dust, you get a lot of self-shielding, your dust temperature decreases, dust growth environments just become plentiful, and your dust mass increases, but the amount of energy to heat that crazy amount of dust mass to sufficiently high average dust temperature would become more difficult.
Oh, I just want to ask, why there's a gap between redshift 4 to 8 galaxies and theoretical prediction, the solid line?
So the solid line, this theoretical prediction, is simply the most massive galaxy they found in a 100 square arc minute box, and then I presume quite efficient dust growth in this galaxy of dust to stellar mass ratio of 1%. It isn't real life, and it isn't true that even, I think some Rebels galaxies approach a dust to stellar mass ratio of about 1%, but it needn't be true that that's the case. But yeah, they should approach one another. I mean, this should straddle the upper limit, and I think that's happening plus minus a factor of 0.3 dex or so.
So on the dust temperature trend that you see is seeing a mild evolution in higher redshifts. So Harikane-san last week, or 2 weeks ago, came here and presented the same thing. I asked him, because there's also a well-known luminosity temperature correlation. So on that plot, actually have a fixed luminosity to take out the luminosity temperature correlation.
Yeah.
To account for that evolution, maybe a little bit more.
Yeah, exactly. That's not a luxury we currently have because we're...
The evolution is very mild. I'm worried that you're actually driven by luminosity selection.
Yeah. This is true. This is also, you are a true prodigy of Ian Smale. He actually mailed me to say the same thing the first time I showed a graph like this. I don't think the evolution is very mild. Personally, I also want to show you on the right-hand side what it means in terms of infrared luminosity compared to a fixed luminosity. This is 100. I mean, it's a factor, that's 2 orders of magnitude. So I think it's quite important to realize that some of these outlier galaxies can drive a lot of the dust-obscured star formation rate. At the fixed luminosity, it would be interesting once we get large enough samples to see this. One of the ideas, I think, instead would basically be, can these galaxies self-shield? Or are the dust volumes large enough? So maybe as a function of dust mass. So at a fixed dust mass limit, do we see that everything that has a dust mass above 10 to the power, let's say 7 or 8, hovers around this low dust temperature while, but then again, all of this is correlated because we're fitting the dust temperature, and that dust temperature gives us the dust mass. So there's already intrinsic.
Yeah, for my sample, we did the same exercise.
Mm-hmm.
And then we don't, once we fix luminosity, we don't find evolution. But that's the redshift 2 to 5.
Yeah.
It doesn't extend to EOR.
Yeah, exactly. The benefit is we're checking it, so that's good. We're really doing the legwork, like the legwork that was slightly easier to do in the local universe when you can just have Herschel fluxes all across large areas. But here we have to ask for 5 hours of band 9, please, on a single source. So I think that's the way forward. There is some idea that it is indeed, in these cases, low metallicity that allows for very high dust temperatures, while in here indeed it is, optical depth that's driving these dust temperatures. But that's restating what you already said.
Right. Any questions? Well, if not, the thing, come good.